Okay. I started to record. Ooh, okay.
Yeah, welcome everyone. So we have the Beehive community meeting where we invited a speaker from National Technical University of Athens, NTUA, Christos Katsakioris.
Katsakioris, yes.
Yeah, who are
Hard.
doing a very cool work on how to make like on the test bed for experiments with Beehive. And yeah, please take it from here.
Okay, so first I'll try to share my screen. So I guess, can you see my screen now?
Mm-hmm.
Okay, and now as well. Okay, so I'm Christos. Thank you, Dmitry, for the introduction. I'm a PhD student at the National Technical University of Athens. Together with my colleagues, we designed and are now implementing a microVM manager local to a node. So, well, first of all, I have to say that this work is partially funded by an EU project, Aero, in which one of the things that we're doing is that we run serverless workloads on ARM and RISC-V machines. So this is what we are investigating into Beehive as well. So, okay, now let's begin by going through a generic architecture of a function as a service platform. So usually there's a scalable fleet of front-end servers, typically behind load balancers exposing functions HTTP endpoints. The front-end is responsible for forwarding incoming client requests to the appropriate worker node. So the workers are responsible for actually executing users' code, that is, functions, typically sandboxed either in containers or in VMs. Between the front end and the workers, there's a control plane, that is a number of services that is responsible for implementing the decision-making logic, like on which node should the request be routed to, or where and when should the new sandbox be spawned, or other scaling decisions, etc. There's usually some configuration store for storing metadata related to the functions, which may later be accessed by any other layer in the architecture. So in this talk, FaaSCell focuses on the worker node. So diving into one of the workers, we find the process that is responsible for controlling the life cycle of the function sandboxes, what is termed a micro manager in Amazon's Lambda, and which may or may not include some sort of agent within the sandbox itself. So in general, the micromanager provides APIs to higher level control plane components for allocating node resources and for controlling the lifecycle of the sandboxes. So quite a few topics in serverless research are related to exploration and optimization of single node performance. MicroVM snapshotting is a notable example that we're particularly interested in. And there are several works that analyze or optimize the performance in this context. Other examples include resource allocation on a single node, be it sandbox caching or keep alive policies, or pre-allocation algorithms for local storage or networking to be used by function sandboxes. So we see that intra-node is important. The research exists and is important. So which system should we use to focus for such cases? So let's begin by first figuring out what are some desired properties for such a system. So first and foremost, we want to be able to focus on experimenting on a single node, which is our primary research goal. So to do this, we need a stack to be realistic, but we also need it to be as simple as possible. So ideally, we don't want to be tied to cluster components that are not necessary for such cases. Second, we need a platform that includes some sort of node local component that is extensible enough to be made capable of local decision making. So, for instance, a plain runtime is not a solution by itself, since we still need some component to control it, providing decision making logic. Finally, we need support for microVMs and microVM snapshotting by the underlying virtual machine monitor, the VMM. And ideally, we'd also want snapshot management support at the platform level as well. So we evaluated several options, beginning with Apache OpenWhisk, one of the most popular platforms for serverless research. So OpenWhisk features a clean and extensible architecture comprising few moving parts, including the invoker, which is a node local component that can be extended with local resource allocation decision making. However, OpenWhisk does not support microVMs at all. And in fact, it is integrated with the Docker command line client. And it appears that its design is kind of driven by a container-centric logic or by inefficiencies that the project itself has identified to the Docker daemon. So our next option was Kata containers, being just an OCI runtime rather than a complete platform. Kata is relatively simpler to deploy and to hack into on a single node. However, this also means that we'd still need to write a higher level component to control Kata and to provide the resource allocation logic. So Kata supports microVMs and Firecracker that we're particularly interested in. However, it does so on an older version of the runtime, which appears to be primarily versed towards traditional cloud deployments. And in fact, there is a new version of the runtime, which is a complete rewrite and optimized for serverless. However, for now, it looks that it only works with a new custom VMM, the Dragon Ball, which does not support snapshotting at all. And in both cases, in both versions of the runtime, snapshotting is not exposed at the platform level. So finally, we considered vHive as it integrates several production-grade open source components like Firecracker, Containerd, and Firecracker Containerd, Kubernetes and its ecosystem, Knative, Istio. So vHive includes a per worker node process that can be extended with local decision making regarding resource allocation. vHive also supports microVMs, and it also supports optimized microVM snapshotting as a first-class citizen of the system. I'm referring to the record and prefetch optimization, which is cool. However, we find that vHive isn't simple enough for our case. So the vHive stack relies heavily on Kubernetes and its ecosystem. And Kubernetes is great for enforcing best cloud-native practices or for providing off-the-shelf solutions to major distributed systems challenges. But what if we're working on a single node? So Kubernetes comprises numerous moving parts, and this makes the single node stack needlessly complex to deploy, but also to hack into. So ideally, we'd want a platform that allows us to focus on resource allocation experimentation without having to deploy Kubernetes and its ecosystem, as we don't really have the need to scale out at this point. So to visualize this, let's consider a high-level overview of the vHive stack. So here we can see major components like Kubernetes control plane, that is the controller manager, the scheduler, the API server. We can see etcd, also the Knative control plane. So we also talk about, we refer to components of the data plane. So we include the autoscaler and the activator. And we can see Istio the front end, and also some components that are local to workers, to the workers, like the kubelet. Kube proxy is missing from this figure. We can see the Hive CRI as well as the two container runtimes, container D for regular containers and Firecracker container D for function microVMs. So stripping this figure from everything related to Kubernetes and from the parts of the vHive CRI that we don't need for our kind of research, what we're left with is a micromanager that we find significantly easier to deploy, but also to develop, to debug, to extend, to understand, and to identify performance bottlenecks in. So this is where FaaSCell fits into this picture. So let's briefly go through the life cycle of an invocation request in FaaSCell. So a request flows into a request source, arriving to the dispatcher, which forwards it to one of the available workers, each of whom is associated with a single microVM throughout its lifetime. So the worker is responsible for contacting Firecracker container D to control the lifecycle of its microVM, and also the worker forwards the request to the function inside the microVM, collecting the respective response, which is then forwarded to a response link. And this is the skeleton of the data path. So how does dispatcher know which worker should it forward the request to? It asks VMpool, a core component in our system, which we attempt to make it as extensible as possible with intra-node, intra-server scheduling policies. So the VMpool is responsible for managing the workers and the VMs, be they busy, idle, persisted in snapshots, or shut down. And it is also responsible for assigning local node resources to them, like CPU time or enforcing memory limits. VMpool's keep alive mechanism can be extended with policies that dictate how long should its microVM remain idle, while the snapshot manager is meant to be extensible with algorithms that place microVM snapshots among different configured devices across the storage hierarchy. Finally, there's a performance monitor that exposes APIs to the worker for collecting custom metrics. So in the past, we've had the need to extend the kernel to extract information that related to the execution, function executions in microVMs. So we thought that a generic interface that can communicate such information back to the local orchestration layer, it would be useful, very useful. Okay, so we aim to use FaaSCell to continue our research on snapshots, on microVM snapshotting, which has been thoroughly studied and shown to be a viable mitigation to the problem of cold starts, as it improves performance by avoiding to boot a sandbox anew, while it preserves DRAM resources by avoiding to keep the sandboxes up and idle. However, snapshotting still suffers from performance overheads, which are mostly related to page faults. And in our prior work, we have identified that these overheads are depend heavily on the storage medium that backs the snapshots. So we tested, our test cases were an Optane NVMe SSD, an Optane persistent memory, and a flash SSD. So we identified several characteristics, like how in some cases certain fast storage devices can practically eliminate cold starts, or how directly accessed devices like persistent memory helps preserving um, the precious and expensive DRAM resources. So we believe that there is room for intelligence in how snapshots are placed among the devices across the storage hierarchy. Our next step is to work on the snapshot manager and the performance monitor to create algorithms and policies for placing microVMs depending on the function that they're responsible for executing. So each function may have several characteristics that change its behavior when restored from a snapshot, like its memory access patterns or the concurrency of the execution of the function or the frequency of such invocations. So moving forward, we realized that we have a need for generating invocation request distributions that refer to realistic workloads. So this brings us to the first discussion point as well. So we are aware of the Azure Functions trace, but we don't know of any tool that is capable of combining the data from the functions trace with some serverless benchmarking suite to produce an overall setup that mimics an execution environment, a realistic execution environment. So most request generators out there really use dummy functions, like functions that sleep or that spin on CPUs. So we wanted to ask the community's opinion about that. So does anyone else have the same need? Is our need for a request generator with realistic workloads that actually have some memory patterns, is it a need that only we have for snapshotting research, or are there any other topics that would be interested in such a request generator? And how important would it be, in your opinion, to factor in every information that there is on the trace? So far we have request generators that take into account the burstiness of the functions, the inter-arrival times, but all the functions do is just sleep or spin. So maybe is there any point in sacrificing some precision of the requests in order to gain something else, like a realistic memory pattern or something? What do you think? Does anybody have any opinion on this? Or should I move on?
This is a good question. These are a good question, and this is something that we have been thinking about for like a year or two. So I think there are two opposite ways of approaching the problem. So one is like bringing in real world benchmarks, making it a standard, making it like something that we can reliably use. And the other way is actually building, let's say, synthetic traces, synthetic like simulated work and this type of approach, so that you can actually isolate certain behavior and study only that. So for example, if you want to do a scheduling research, like you want to zoom into scheduling policies or placement or scaling, the question is, how important are the phenomena that appears on worker nodes as opposed to phenomena that appears in the cluster infrastructure, for example. So, and what we think so far, I would say in my group and like ETH, people are also working on that, is that so far we study the cluster level phenomena, which means how efficient the control plane and request placement and scaling, how timely it is, and so on. So it's mostly about studying the queuing effects in the cluster. So from that perspective, we're not so interested in effects and the worker nodes. Yeah. But at the same time, to bring it to a more realistic scenario, what happens on the worker node, you do need, like in terms of like memory interference, cache interference, and so on, you do need real workloads. So it's about this. So from the perspective of scaling, we are releasing a tool soon that can play Azure traces. But the problem there that we faced immediately is that Azure traces are actually collected from a huge
cluster. Or, yes.
Yeah, from a huge cluster, you need a lot of nodes, a lot of cores. So by some rough estimates, I think it's at least hundreds of nodes that you actually need to use it. So we try to sample down these traces so that we can still have all the queuing effects and burstiness and all these things in the trace, in this sampled trace, so we can still make conclusions on like scaling policies efficiencies. So this tool we are releasing, and we want to make it like a standard tool for benchmarking scaling stuff. It's called the scaling part. Because actually there are many papers and they all cherry pick different functions, usually from the same exact trace, because they cannot play the whole trace, and it's absolutely impossible to compare it. So everybody takes their own trace and then tries to kind of reproduce the results from the previous time and compares. So it's literally impossible to compare one paper to another sometimes.
Yes.
Yeah. So this is something that we kind of addressing from this side. Swarm is something that I think is more appropriate to use at the worker node. So for example, if you have set up like you described, like FaaSCell, so what you care about is just the traffic that goes to these workloads, and you just assume like a random mix of workloads, for example. Then probably you can just take some traffic from this this loader infrastructure that we built that downsamples the Azure trace and play it on your mix of workloads. And then you can see the effects on the node. So from that perspective, so in the recent paper from Edinburgh, actually, David is also here, actually, the main author. So they used a lot of leaf functions. So as opposed to like big functions with multi-function
function chains, etc.
Yeah. So they use just leaf functions like AES and authentication and so on and so on, so that they can compete for the cache or for a branch predictor or for something else. Actually, David just got another paper accepted, I think, about branch prediction actually in micro. So this is another announcement.
Great.
Which I think
great.
works.
Congratulations.
Yeah. So keep your eyes stay tuned for this new work by David and Boris and others. So it's gonna be micro is the next, like in a month. Yeah. So
so that sounds very interesting.
We're also thinking about, like, for example, data intensive applications. How do you model I/O, or like disk I/O, or like I/O, like network I/O and things like that.
Yes.
And for snapshots, I think this matters a lot, actually. And for that, the vHive stance is so again, like either you do everything properly, like everything, which means like storage for snapshots and how you move them and deduplicate it and whatnot. So there are actually a lot of problems that we didn't even touch in vHive, like how to store guest memory is actually the totally open question that and vHive also currently doesn't really support remote snapshots, in the sense that you capture on one node and restore in another node. So this is something that we have made progress on, and maybe by the end of the year, maybe like let's see. It almost works right now, but let's see. Yeah.
Okay, that's very interesting, and in fact, it brings me to the second point. So, uh, so whenever we talk about the system, everybody asks us, okay, and how does this scale out? So, we understand that a function as a service platform is meaningless if it doesn't scale out. For now, we focus on single node and snapshotting, but eventually we aim to scale out as well. And we've thought about integrating with a vHive stack or generally with Kubernetes, maybe some other combination of components of the Kubernetes ecosystem. However, at the same time, we're not really sure whether Kubernetes is the right step for scaling out. So back in Sesame 23, Lazar Vetkovic gave a great talk and some very interesting points against Kubernetes for function as a service platform. And we're interested in your opinion. So vHive has chosen Kubernetes, and now you have experience with Kubernetes in serverless and with related overheads. Is it something that maybe you're thinking to change or to improve? Maybe. I mean, what's your opinion on Kubernetes for function as a service now that you've experienced it?
So Kubernetes was built for like long-running workload. And what we are currently working on is making like a cluster manager Kata for serverless. We also have like a SOSP workshop paper, like words that will be public soon. So you can have a look into what actually
Great.
we work on and what we think. And yeah, we are currently working on a system that will be a substitution to it.
Okay,
But
that sounds very
yeah,
interesting.
obviously, Kubernetes suffers from high overhead in the context of serverless. As I said, long-running workload. For example, Nginx server, you run it for 5 months. You don't care whether you pay some initial costs or not. It's amortized over long run, but this is not the case for serverless workload.
Exactly,
Yeah,
exactly.
it's a great point. However, like I want to defend Kubernetes a little bit as well because you know, in the old time, like let's say a decade or two ago, people were questioning Linux if it's the right operating system for highly available services, and people were doing a lot of kernel bypass and RDMA and all these things, and DPDK, like all SPDK, all these things, and then it always comes back to Linux. So nobody really uses this fancy kernel bypass systems in practice, actually, just because you get like a lot of flexibility, a lot of kind of the whole package that you need. And Linux got faster. So if you take a look at the papers that were comparing to Linux CCP, I don't know, from 20 years ago and from now, like the Linux networking stack became way faster, actually.
Way faster, yes.
So I think for Kubernetes, it's also it's a huge operating system for the cloud. So you can replace it, and essentially you're building some kernel bypass kind of techniques, right? Or you can find a way how to adapt it, I guess. So these are two approaches that like one may win, but it's difficult to say which one, because I think it's still early for this operating system, like distributed operating system like this one. It hasn't been enough time, I would say.
Yeah. Okay.
So in
Okay.
our group, we actually try to take evolutionary approach, actually. So we're trying to figure out how to work out the interfaces between kind of the worker nodes and the cluster infrastructure. for example, and see if, like, for example, for every query, do we actually need this global brain to be engaged or not? So that's the question, like, that people need to think about, I think.
And also, just to add here, there's some work on scheduling, and so well, I didn't put it correctly. There's a lot of work in scheduling, and some of it refers to function as a service. So there are many papers that defend different opinions about which decisions should be made locally and which should be made globally. From a each node resources, should they be allocated by a cluster-wide scheduler or by a local resource manager? We believe that this is an open question. We probably believe that there's certainly room for decision making locally. This is why we make it. So which decisions should be made locally and which globally is a question that we're trying to figure out. It gets a little bit complicated if we take into account the various keep alive policies and especially snapshotting, or what resources can be shared among snapshots, etc. And there's certainly room for improving scheduling over Kubernetes with that respect. I mean, it's something that we believe that makes sense, and Kubernetes provides extensions for to extend APIs to extend the scheduling. So I see what you're saying about the evolutionary approach, how Kubernetes can be modified to adapt to such needs.
Yeah. I can give you one example of how allocators work today. Like, pretty much most allocators today, they face the scalability issue. So the way it was solved, that like if every process asks the system to like give memory, so like in the old times there would be like a big block that kind of gives memory, right? So what people figured as a solution is have arena allocators where each thread or each process has like pre-allocated buffer memory, and they just need to make sure that this buffer is like not empty or like with high occupancy, let's say, so that the calls into the system are actually minimized. And that was the like best solution that people converged to. Like, so they didn't really go the way, like all the way to like removing allocation from like the system stack, even though like, yeah, still there are some approaches like this. And there was a paper there was a paper in HotOS talking about giving an allocator a separate core. So yeah, there are different approaches. So I think we should look at our system from both perspectives and see what makes sense.
Okay, I agree. So the last discussion point is purely technical. It's something that we haven't really looked into, though it somehow dictates some design decisions. So at the moment, loading a snapshot requires, so Firecracker must find the identical tap device for networking and the identical, so we're using Firecracker Container D with the device mapper snapshotter. So Firecracker expects to find the same device mapper snapshot block device so that the microVM is still functional. So the naive solution that we're doing for now is we just keep it around as long as we need it, as long as we need the snapshot. However, we've not really tested how well does this scale up on the same node, or what effects may have the performance. Maybe in the kernel, we haven't really looked into it. We don't know if maybe any of you here in the community has investigated. And of course, how does this scale out? So what you said earlier about creating the snapshot on a node and restoring the microVM from the same snapshot on a different node, we're not really sure how does that would work optimally.
Mhm. Yeah, so in terms of performance, like we are very far from that. Like in terms of correctness, I think we are nearing the solution actually. So regarding the tab, there's actually this is a easy question, relatively easy compared to the other one. So regarding the tab device, yes, it needs to be the same in the sense of the same internet, the same IP.
And the
So the
same
solution,
MAC for performance.
yeah. The same MAC and the same IP. Yeah. So how to achieve that? Just another level of abstraction. So essentially, you keep this device the same, but put in a different network namespace. So this is something that we actually merging it right now. So that part is solved. And this is also a recommended part from the Firecracker team as well, actually. So this is something that I would say more or less solved. When it comes to disk snapshots, this is actually a tricky bit. So we have been banging our head on it for quite a bit. So yes, so the easy part is like you need to migrate memory, then you need to migrate, you need to recreate this network namespace, the tab, assign it to the same IP, all these things. And then the tricky part is that you need to move the disk state. And for the disk state, there is some read-only layers, which you can move through the registry, for example. So you just do kind of Docker pull, if you like, container pull. But there is this also a read-write layer that you need to move as well. So we did all of those. So we like built a prototype like this that we are currently debugging. So there's still issues appearing in the file system. So currently we have some ext errors, and we raised some bugs, some issues, sorry, on GitHub of Firecracker, Containerd, and Firecracker. So we can confirm that actually for Firecracker, if you do it directly, this thing works with like a rootfs as opposed to snapshotter. So we actually have a prototype that actually works. If you do everything manually without Firecracker Containerd. Now, if you do the same with Containerd, there is something in the mapper somewhere we're still hunting it down, connected to the file system or disk. There are some ext errors that manifest themselves in. So the VM is still kind of, you can run there, you can do something with it, so it's operational, but the server inside crashes.
Okay, so it's related to the mount,
server.
right? Yes.
It's
So
related
the
to
specific
the mapper for sure. Yeah. So to this rootfs, to this way of managing rootfs. Yeah. So yeah. So when we raised an issue on Containerd, and so far we got a response. So sorry guys, we don't have time. Yeah. So, but we kind of have this feeling that we are really, really close to that. Yeah.
Okay, that sounds very interesting as well.
So yeah, like the summer intern who is working on it is currently wrapping up. So we have a bunch of pull requests already submitted, and some of them will be kind of upstreamed soon in the Hive. So if you guys are interested in this, like we actually feel like we are really close. If you kind of want to take a lead on this, like building upon what we've already achieved and maybe finalize it, that would be even better, to be honest. Yeah, because the internet is wrapping up. So, and I think we are really, really close. If someone just sits down and spends a week or two, maybe you guys can figure it out actually.
Yes,
Everyone's good. Yeah. And we can also share how it works, for example, with Firecracker directly. It's just what's really going to be annoying is you need to prepare rootfs for everything, which, yeah, you basically, if you want to manage rootfs properly, you need something like overlay FS or the mapper. registries. So you cannot really hack it. You cannot really ignore it.
Yes. Yes. So yes, that's very interesting as well. I mean, I see, I do see your point, and I believe that we're okay. 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 So that's all from my part. That maybe you have any questions about the system or anything. Should I don't know.
Does anyone have questions?
So actually, I'm not sure what tap device and DM snapshot is. So if it's okay, can you give a brief explanation about this too?
Okay, so the tap device is a virtual networking device that is used by Firecracker to provide a network interface. This was mostly a technical question, so there's not much to read into it research-wise. So the DM snapshot block device is a functionality provided by the device mapper, a subsystem in the kernel at the block layer, to provide with a block device, to provide the microVM a block device that can be mounted and be used as the container's rootfs inside the microVM. And it does this efficiently. So that's it, essentially. I don't know if it makes any sense.
So essentially, it's like the only two things that microVM is doing. Actually virtualizing one single network device and one single block device.
Yeah.
Right?
Yes.
Yeah. So
Okay,
It's
thank
just
you.
the dev mapper is the kind of it exposes an overlay FS as a virtual device to a Firecracker microVM. So it's kind of the host infrastructure. So it's not managed by the hypervisor. It's managed by the host. Essentially, it's similar to Docker overlay FS device mapper.
It's like overlay FS, but at the block layer. That's the main difference. But it's the
Okay.
same idea.
Thank you.
At the block layer. Oh, by the way, yeah, we also have support for eStarGZ actually, but only for containers. I don't think we tried it with Firecracker actually, because this is something also very interesting, I would say. Managing at the block level as opposed to like an entire layer.
Yes, it's very interesting. I don't know if you've studied the latest paper by the Firecracker team on ATC 23. They describe the way they pull the images. It's very interesting. I can't recall the details right now to share, but it's a very interesting read and somewhat related to that.
And it's very easy to find because it's the best paper.
Yes.
Yeah. So yeah, we talked about this paper actually. So yeah, it's container support and the way they do it at the block level and things like that. So it's very similar to what eStarGZ does. StarGZ. And this is something that Docker or Containerd are adopting already. So, and I think there was some proposals on like prefetching or something like this. So like you basically leveraging spatial and temporal locality on this. Yeah.
Very interesting topic.
I think what's also very interesting there is that like there is a storage management, there is also, I mean, disk management, disk state management, there is guest memory management, and it's currently not very clear how it all comes together. And container support at AWS is only about disk state actually. So there's still work to be done. Ooh, yeah.
So
that was very interesting discussion, and yeah, thank you for making it interactive. I think it's It was very nice and thought-provoking.
Thank you for the
Hopefully, we also
invitation.
were able to answer some of your questions as well.
Yes, yes. Thank you both for the invitation and for the discussion. It's been very, very fruitful. I've noted down some stuff while we've been talking. It was
And
great.
regarding remote snapshots, you can contact us, and then we can think about it.
I definitely will, and of course I'll keep an eye on.
Yeah.
I've been stalking the development of the Hive anyway. So great.
And thanks. And we also have open PG positions, just to say.
Okay.
Cool. Nice. Does anyone have any question? If so, I think we can wrap up. Thank you very much, everyone. So we can just post it on YouTube with minimal editing, I think, if nobody minds it. All right. Thank you.
Thanks a lot.
Have a great day, evening, morning.
Thank you very much all. Bye.
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 Bye. Bye.